All right, woohoo! All right, nice, very nice. Okay, so max flow, we did this last time, or at least some of it. We talked about this greedy augmenting path algorithm, and so the idea is you have this flow problem. You're trying to route as much flow as possible. We already have these tools, even from 61B, of finding a path. Right? You want to go from A to B, you can do that. From going from S to T, you can find a path from S to T. And now, if you want to route flow there, you can route some flow on the path. Okay, so we do that, and that's the idea of the algorithm for maximum flow. Is you find a path from S to T, and you route flow along it. Okay? You find a path where you can route flow on it, which means that now if you wanted to do it again, you want to say you don't find the same path again. So you have to update the amount of flow you can send on each edge because you've already sent some flow along each edge. And then you try again. You find a path among the edges which still have some capacity left. Right? That's the idea. But that doesn't really work. So what we do is we say, well, in fact, what we're going to do is we're going to say, maybe we made a bad decision in routing the path. We're just routing any old path. It could be a really bad path to routed flow along. You may have been wasting resources, right? You could use a very long path, for example. There's no real guide here. It's greedy, in a sense. But this reversing, this adding of residual capacities, which is a big idea, and it's a little subtle, and there'll be an exam on it, right? I mean, it'll test this concept, and it's just a little subtle, but it's not too hard. Is we just say, look, well, when we route flow along one way, let's say we could undo it by just simply routing flow the other way and adding capacity to undo that decision. That's what the residual graph is doing. Okay? And now the question is, like even now you're like, oh, if I undo everything I did before, why am I making progress? Why do I make progress if I'm undoing stuff? Yeah, let's try you. Yeah, because each path at least sent some flow from the source to the sink. So that when you undo it, you find a new path, you send extra flow. So something keeps going up. The flow that you sent keeps going up. So that's progress, right? Okay, so there has to be a notion of progress. You just can't undo everything. Okay, so that now the optimality condition, which I'll prove today, is that if there's no augmenting path in the residual network, that means there's an ST cut that one can find. When is there no path? If I can't find a path from S to T, what does that mean? It means the graph is kind of disconnected, right? That's sort of what, there's no directed path from S to T, so there's a cut for which there's no edges across that cut in the residual network. Okay? Now that cut will correspond to a cut whose capacity is equal to the flow path value, and I'll show you that. Okay? So now what we've done is we found a flow and a cut with the same value, and it's clear that a cut is an upper bound, or I'll show you again. A cut is an upper bound on the total amount of flow you can send, because if you cut all the arcs across this cut and in one direction, you can't possibly have sent more flow across that cut. Okay? Yeah. Yes. Yeah, I show you. Nice, very nice. Yeah. What he asked is this really the same algorithm as simplex in some way of writing down the variables and updating the variables? Is it like going from a vertex to a neighboring vertex, right? So let's think about it at the beginning. What was the beginning of simplex? You have 0. What are the variables here? There's a variable for every edge. And what are all the edges? 0. Right? And that satisfies all the constraints because there's conservation, right? So, you start like simplex at least, right? You start with all zeros. And at least you start like simplex in the way I did it. Okay? And then now the question is, y is a path like going on an edge linear algebraically. Like linear algebra is funny. You ask the leading researchers in the field, they're like, I don't understand linear equation solving. Because it's super powerful, right? All of a sudden you do this set of mechanics and all of a sudden you solve this problem. And it's crazy that you do that. So, but this one, it shows you what linear algebra, how the linear algebra is doing in this combinatorial setting. Okay, so now that what I am going to show, it's a little bit complicated to show the simplex method here. So I'm going to show you this maximum matching problem. And I'm going to show you that this maximum matching can be done by reduction to max flow. It's not stable marriage. It's maximum matching, so don't get too worried. And there's sort of a path-based argument for maximum matching. That algorithm, I'll show you completely that it looks like simplex. Okay, so this is a flow network. We saw this last time. I just took out all the pauses, the reveals, or whatever. So there's capacity constraints, and again, like he said, there's variables, f sub v. That's your solution. Okay, and there's constraints, which these are numbers. These are not variables, right? That's the input. Okay, so it says for every arc, your capacity has, each arc has a capacity, or edge has a capacity. It says that for every vertex, the flow in should equal the flow out. That's flow conservation. You're not losing flow somewhere in the middle of the network. There's no leaks. And there's all versions of this with leaks and all this stuff. You can even see how to modify these things. And you want to maximize the size, which is the flow out of the source, which equals the flow in the sink, which is an exercise to see why that's true. I mean, basically it's true because where the flow can't end up in the middle, so it must end up at the sink. Okay? And now the question of whether it's optimal. In this picture, what I did is I showed you a cut. And I showed you a cut is a partition of the vertices into these 4 vertices on the left and the 2 on the right. And now I look at all the arcs that go from left to right, and I add up the capacities. And there's 1 plus 1 plus 2, which is 4. And the value of this flow is also 4. It's 1 plus 3 if you add the blue numbers over here. Okay, this is the value of the flow. Questions? Everybody remembers this? Or everybody saw it in discussion? Okay. So an ST cut is a partition of V into S and T, where S is in this subset. Big S is big S and big T, where little s is in big S and little t is in big T. Okay? And its total capacity is the capacity of the edges from S to T. This is just generically what it is. Okay, so here you go. Let's just see if you remember. Is that a valid flow? Because we saw this last time, right? This is too big. And is that a valid flow? No, because the flow into here is not equal to the flow out. And this is not S and T. Okay? Okay, so here's the algorithm. Again, it's a linear program. So the variables f of v is the linear constraints and the linear optimization function. Everything is linear. Like, I don't care that it's in standard form. You know how to rewrite it in standard form if you want. So that's cool. Okay, so now it happens to be integer, and I said this last time too, because you can talk about subdeterminants, but in fact the algorithm also gives you a proof of this, that the value is integer if the inputs are integer. Okay, and the algorithm is a simplex method, so it tells you that there's always an integer solution. Okay, for this linear program, this is not true in general. It really depends on context. In general, the solutions of linear programs aren't necessarily integer at all, right? This is only for this problem. Okay, so here's a simplex method. It is a simplex method. Okay. Okay, so you can do this. There you go. I found a path from S to T. It's just an arbitrary path. It could be produced by depth first search, this path. And it finds a path here, right, given the right adjacency list ordering, right? So So now the capacities here, I'm going to try to send, how many units of flow should I send along this path? 1, right? At least, at most 1. Because if I send more than 1 unit of flow along this path, then I will violate this capacity constraint. Is that clear? Okay. Okay, so I send 1. Now I update the remaining capacity constraints, and I say, okay, well, I already used 1 unit of capacity here, so I could only use 3 now, and so on. I used 1 unit of the capacity, which was the black number. The new black number, or the capacity, is 0. Okay? And so on. And let's run that algorithm. And this is the, here again, I find, okay, first of all, what's the optimum for this? I want to do it on a small example so it's absolutely clear what one should have done. Okay, what's the optimum solution here? 2. And does everybody see the paths that one uses? Right, or the solution? The solution is to route 1 unit of flow along the top path and 1 unit of flow along the bottom path. And now we know that's optimal because the cut here is 2. Right? So size 2. Okay? But I'm going to do something dumb and route flow along this direction. Okay? And so now I'm going to do this algorithm, which is this update the capacities of the path, of the edges, because I already used 1 unit. Another sort of question is, what is a path? Why am I routing, when I say route along a path, what it says is I route 1 unit of flow along every edge. Okay? And that preserves something. What does it preserve? If you look at the conservation constraints on any node in the middle, you route 1 in and 1 out. So the conservation constraints were satisfied before by the previous function. They're still satisfied on a path. That's the property of a path. Does that make sense? Okay. So in particular, what I'm saying is that it satisfies all the linear equations, the conservation constraints, which are linear equations. So this solution, this notion of increasing this and increasing this, make sure that the constraint that says the total flow in minus the total flow out of A is 0. So it satisfies a linear constraint. So this path is staying in a subspace. Okay, it's staying in the subspace where all these constraints are satisfied in this big m-dimensional space. Okay? So that's what I'm saying. So this is a picture of linear algebra in a very simple setting. It says, look, what does it mean to stay in the subspace? Is all the conservation constraints are satisfied? A path will obey that. All the conservation constraints in the middle. A path from S to T will move in this subspace. Okay? So it's sort of a nice, sort of simple example of just linear algebra. Okay, moving inside of a subspace where these equations are satisfied. Okay, but now we're stuck, right? Now, if I look in this network, this directed network, I don't see a path from S to T, right? So in discussion, you saw, and last Wednesday, you saw, well, this is not the whole algorithm, right? The whole algorithm is now not only to say I can't send more in this direction, but I can send more, I could sort of undo this decision. So I'm going to add an arc here. Is I'm going to I can reduce the flow here. Okay, but that's weird. Like, it's a little weird. Say I just set this back to 0. What would happen? Yeah, that guy would not satisfy the linear constraint anymore. Right? If I set this to 0, there would be 1 unit of flow going into A and no units of flow going out. So it breaks the linear constraint. So, but what I'm going to do is say, well, I could send flow back here, but I have to obey some more constraints. I have to really now route along a path in this network, in this residual network. Okay? And so what I could do is if I send 1 unit of flow here, I sort of have an extra unit of flow here. Okay? Now, the way I can get rid of 1 unit of flow is I could just get rid of it on this edge. And now what that does, the effect that has is it sort of makes the flow appear at A. Okay, so that's the same thing as pushing flow along this arc. So adding the residual arc really is giving you the opportunity to, when you push a flow into here, to get rid of it by get rid of the flow that came from here and making it start there. Okay, so that's what the residual arc is sort of capturing. Okay, and then you route along this, and now when you update everything, you get the solution that you all saw at the beginning. Okay? Okay, and you could do this here. You can do it. It's hard to draw this many arcs in opposite directions, so I drew them all on top of each other. But you can see an algorithm here. But each time, the black numbers are the forward capacities. The red number, the flow here. The blue numbers are the flow, and so you can keep seeing it. I didn't put the reverse arcs in. Okay. So you can just see it happening. So for the first path, it looks like this. I found a path. Now my second path looks like this, right? This is a path with positive, that's the capacity 4, capacity 3, capacity 1. So I can send flow that direction. And now I'm updating everything. You got to watch it, whether I do it. And so here there's capacity 1 here, capacity 2 here, capacity 1, capacity 4. I could send that capacity 4, I sent 1 unit of flow, so that went down to 3, for example. And then there's this other path here. There's a positive capacity, positive. Okay, and now I'm optimal, right? There's no path from here to here, right? This arc is 0, this arc is 0, this arc is 0. That forms a cut. Okay, so we could check the result, and here's the result. I'm just going to check one edge for the capacity constraints, and I'll check one node for the one vertex for the conservation constraints, and you can look at the thing. Okay, and we have this is the example and the solution we got before. That was the algorithm to get the solution. Okay, so now, okay. So there's the capacity constraints. So now I want to say I got a feasible solution, right? So what does a feasible solution mean? It means I have to have a function f of e where every f of e is less than c of e. Okay? So I only increase flow to c of e. That's the idea. And I only can use the reverse arcs to decrease it to 0. The reverse arcs only put a number on it that corresponds to the flow in one direction, and you can only send that much back. So the net flow will be 0. Okay? Okay, so that tells you that all the flow values will be between 0 and C of B. Okay, so now you also have conservation constraints. That says the flow into a vertex is equal to the flow out of the vertex. And the algorithm adds a flow, some flow f, some value f, from every edge from S to T. Now, every intermediate arc, one of those edges goes into every intermediate vertex. One of those vertices has an arc that comes in, so F units come in, and F units go out. So it preserves the amount of flow coming in minus the amount of flow going out is equal to 0, right? F minus F is 0. Okay, so now you want to show that it's optimal. So now I want to say, first of all, let me prove this theorem. I stated it several times, but let me just prove it. The capacity of any ST cut is an upper bound on the flow. I actually argued the proof. Let's C of S to T be the sum of the capacities of all the arcs from S to T. So it's this expression. Okay? It's the sum of the edges from where one endpoint is in S and one endpoint is T of the capacity of the edges. So this is not about the flow function. Right? It's just, it has no flow function here. Okay? Now for a valid flow, the flow out of S is equal, out of this whole subset S is equal to the flow out of little s. Why is that? So what I'm saying is the total flow from this left side of this red line is equal to out of it across all of these edges and the flow out of it is across all of these edges out of it. These black edges illustrated is equal to the flow out of S. Why is that? For any valid flow, that has to be true. Why is that? Yeah. Because the conservation constraint, but right? So what I'm saying, let's add the conservation constraints for all the vertices in S. But now I'm adding it for all the vertices in S, including. This is a conservation constraint. This should be 0 for all the vertices except for S. S doesn't have to obey the conservation constraint, right? So I'm saying here's the flow out of the thing minus the flow in, right? That's how I'm writing the conservation constraint. Now, these are all. So now let's look at an edge. Okay? Okay, so where will the edge, if there's an edge between two vertices in S, where both endpoints are in S, what will happen? Well, it'll appear as a positive variable for U and a negative variable for V. So you add the edge in one of the vertices for V, you add the flow variable, and now for that same arc, it will appear as a negative in this thing. So what you do for any edge between two vertices on this side, you both add it for one end and you subtract it for the other end. Okay? But now for the arcs in the cut, you've only added it. Right? You've only added the outgoing arcs. So this tells you this sum over all the vertices in S is equal to the sum of the edges in between these two of F of V. Okay? And that's just a conservation constraint. I mean, maybe a simpler way all it's saying is that the flow starts at S and can't be anywhere in the middle, so it must go across these edges. That's another way of saying it. Okay? And the same argument is over on the left-hand side. The right-hand side. Okay, so the flow out of S, this is the upper bound. So for this cut, for any valid flow function, for any cut, if you write this expression, it is the value of the flow. It's exactly the value of the flow. Okay? And now, so this is the value of any valid flow. For any cut, the value of that flow is the sum of the edges between this cut, on the two sides of the cut, of the flow values. Right? Now, what is each one of these upper bounded by? F of E has to be less than what? C of E, the capacity of the edge, for a valid flow. Okay? So, so it's less than or equal to the flow across the cut in one direction minus the flow in the other direction, right? You could actually send flow back. Okay, where did I do that? So it's actually technically this edge here. If the flow across this cut is all the flow in one direction minus the flow in the other direction. So for any arc from T to S, that's also that reduces the flow across this cut. Okay. Okay. So now each one of these values is less than C of E, and let's just upper bound this by 0 because it's being subtracted. So we know that the sum of these flows, the sum of this flow, has to be less than the sum of C of E, which is equal to the cut size. Okay? Okay, so, it's an argument. It's not, if you actually did it in matrix form, you get exactly the weak duality for the linear program. Okay? If you wrote this all down as a linear program, this is the same argument as the weak duality. You use the feasibility of the primal to show this upper bound. Okay. So now finally we want to say that, okay, so there's no path. At the termination, when do we stop? We keep routing a path as long as we can until we get stuck, meaning that there's no path from S to T. Okay? So there's no path, right? You just keep routing. You find a path in the residual network, you augment along it. You find a path in the residual network, you augment it along it until there's no path with residual capacity. Okay? So what does that say? Depth first search starting at S does not reach T. Okay? That's what you're saying. Okay? So when you do depth first search, you do find all the vertices that you can reach. right? And then there's some vertices you don't reach. So does that tell you a cut? Does that give you a cut? There's all the vertices you reached from S and all the vertices you didn't reach from S. And the vertices you didn't reach from S included T, right? Because there's no path from S to T. Okay? So if you do this, you'll get a cut like that. There'll be some set of vertices you can reach from S, and that's the ones on the left-hand side of this red line. And then there's the rest of them, which is what I'm calling big T. Okay? And what I'm saying, what does this mean, this property that there's no residual capacity leaving S? It means that every one of these arcs, what is their residual capacity? Every arc from left to right, what is their residual capacity? 0, right? Does that make sense? So for every one of these arcs, how much flow do you send across it? If an arc has capacity C of E, how much flow did you send across it if it has no residual capacity left? C of E, right? Does that make sense? Okay, so it says for a flow, when you're done, every one of these black arcs is full. Okay, so the flow value equals the capacity. Right? Okay. Now what about this arc? How much flow can be sent back on this arc? My current flow solution. What I'm saying is I'm starting right now, I have F sub B's for each edge. So I have some flow value on this edge. Right? And I'm telling you that that the residual capacity of the arc in the reverse direction is 0. Right? That's the other way. If it was non-zero, then I could expand my depth first search and go across the reverse arc here. Okay? So what must it be? It must be 0. Right? Does that make sense? So this is a subtle thing. It's slightly subtle. It better be if I did a depth first search in the residual network, if this was non-zero, if this flow value was non-zero, what would be the residual arc in the opposite direction? It would be non-zero. There would be some non-zero capacity there. If it's non-zero, then depth first search would cross this cut, would search across this cut. Okay? Okay, so no arcs so all the arcs leaving S are full. No arcs back into S have any flow on them. So the total flow leaving S is the capacity of C times T, right? If you sum up all these FEs, what you're going to get is a total flow from S to T, and each one of these, the black ones is C of E. Each one of you subtract the ones coming back, and those are 0. So valid flow means all. That's what we said before. A valid flow means all that flow is from the source. So the value of the flow is exactly equal to the sum of the capacities of these edges, which is the size of this cut. Okay? And we know that the optimal is less than or equal to the size of any cut. So now I found a flow whose value is equal to the value of the capacity of this cut, and I know for every cut, the optimal is at most this much. Okay? So that means the flow is maximum. Okay? So, yeah. So cut is and now why is this a minimum ST cut? Yeah.
Because otherwise there would be a cut that's less than the max flow.
Yeah. Okay, so now I'm saying I've produced a flow and a cut with the same value. The cut value is an upper bound on the flow value, right? So if there was a smaller cut, then it would contradict the fact that this flow was this large. Right? Every cut is an upper bound. Okay? So this is called the max flow min cut theorem. So any flow is less than any cut. This flow is equal to this cut, and therefore the maximum flow and the minimum cut. So this is kind of very nice. It's a very combinatorial algorithm that's really sort of doing some sort of linear algebra underneath in terms of this linear program. Okay? Okay, this is celebrated, so you're supposed to celebrate. Okay, that's celebrating. All right, let's actually celebrate. Okay, I was going to get a party hat, but I was late. Okay, so that's it. Okay, sorry. Did you guys ever... I always wanted to be Napoleon Dynamite. Yeah. Okay, so, why does the algorithm terminate? Because the flow keeps increasing. So termination means something, you can always make progress, the flow keeps increasing. You already said this on the first slide, but it's good you're seeing it again. So how long does it take? Okay. In terms of the number of vertices and number of edges, how long does it take? Well, I don't know in terms of the number of vertices and number of edges. But I know that every step, at least I send one more unit of flow. Okay? So it could be order m. Each step is routing a path. How long does it take to find a path? It takes order m, right? You have to look at all the edges to do a depth first search or a breadth first search. Okay? And the total value of the flow is f. Okay. Okay. So now, is this efficient? That's the question. And this goes back to the very first lecture about what does efficiency mean, or it's sort of in computer science we're obsessed with it should be small in terms of the problem statement size. Okay? So here, what's this problem statement size here? Well, it's not so big. It's like there's like 7 digits on each edge. There's 10 edges, so it's about 70 or 80 digits of to express this thing. Okay? But how long might it take to route the flow? Is it going to be small compared to the 70 or 80? Or not even 70 or 80, it's 40, right? Yeah, so what you could do is you can do an algorithm like this. The first thing, I can do this dumb thing and send one unit of flow this way. Okay, that's 9. Okay. Yeah. It's very sad. Yeah, so it's really sad. I maybe should have made it longer so we would be sadder. But, okay. Okay, so there's a way to fix this. Okay, and this is Edmund's Karp. Karp is a famous Turing Award-winning professor who was here and recently retired. So you can augment along the shortest path. So this by itself makes it better. Okay? In particular, it's just breadth first search. Instead of doing depth first search, you do breadth first search, and the algorithm would be much better. And you can see it in this example, right? Like this path is longer than the shorter path. So it's actually clearly a bad choice here. But that's sort of stupid. I can make this other path longer, so at least locally it doesn't. I would still choose this path by adding vertices in the middle. But still, generally using a shorter path you can prove better things about it. And let me show you how. Or let me say, if you use this algorithm where instead of routing along any path, you route along the shortest path or the breadth first search path. It's not shortest with respect to the capacities. It's just breadth first search shortest, fewest number of edges. Then you could do it in order v times e augmentation. So this is polynomial time. And now notice it doesn't have any notion of how much flow you're sending. So the actual values of the flow values on the edges don't matter at all. They could be really large, and still, if the network is small in terms of the number of vertices and edges, this will be fairly fast. Okay, so what's the idea? The idea is that, one idea, there's some heuristic ideas, is you're using as little of the capacity of the network as you can by routing along the shortest path, right? Each edge is a resource. Every time you don't want to use a lot of resources to get from S to T, you might as well use as few as possible. That's sort of the intuition. The analysis is that, well, at some point you have some distance from the sink. Okay, that's D of V. And you only route flow on U of UV if the distance from U is larger than the distance from V. It's greater than, actually strictly greater than. It should be a strictly greater than. Okay? So in some sense, let's think of it as a hill. T is at 0, and S is at whatever distance it is away from the sink. And you only send flow downhill, is what it says. Okay? But, okay, so now the problem before, when you saw that network, is I send flow back and forth and back and forth. I keep redoing, I do this, I send this way, then I send that way, I keep undoing it. So the problem is when you reverse. So if I send flow one direction along an edge and I never send flow in that direction again, I'm done with that edge. Right? If I only send flow in one direction, at some point it fills up and I'm done with it. The problem is when you reverse it. Okay? And then you reverse it again. You keep doing extra work when you reverse and reverse and reverse. So the point is, if you send flow from U to V, V has to be lower than U. Now if you send flow back from V to U on the reverse edge, then V has to be lower than U. Okay? Than the distance to U. So somehow when you reorganize the network, now the distance for U is farther than the distance to V, from V to the sink. Okay? So the biggest the distance can be is V, is the size of V. Okay? So now that's now you can prove that, well, you can't reverse the arcs too much because you can only send flow along one direction if U is higher than V. You can only fill up one direction once, right? Yeah, I'll get to probably your question in a minute. Okay? So now, with this algorithm, if you augment along shortest paths, what you can prove is the distance from S to T will only rise. Okay? Never gets smaller. Okay? And there's some intuition here. It's like, because the only way it could get smaller is you're sending along a path. If it could get smaller, you're adding the reverse arcs. Now, adding reverse arcs, you're adding uphill arcs. So they don't help you get closer to the sink. Right? When you send flow along the path, the shortest path, you're only sending downhill. So can you make the path shorter? Well, you're only adding arcs that are going uphill. So any new path you've added has to go uphill, which means it's longer than the original path. Okay? It goes downhill to some place, comes back uphill, and then goes back down. Okay? Okay, so every E time, now one other thing it says is when you route one unit of flow, or you route one path, you saturate an arc in one direction, right? You send it as much flow as you can until an arc is saturated. There's no more capacity. So that says you've completely used it up in one direction. The only way you could ever use that arc again is if you send flow in the other direction. Okay? And you can't do that too often because these arcs don't switch directions more than n times. Okay? So there's order V times E removals. This removes that arc at that direction, or that edge at that direction. It may be used later at a higher distance, but at this distance it can't be used again, and it can only be used at higher distances. So the total number of times you saturate an edge, or you use all the capacity in an edge, is V times E. And then each time, V times E edge removals, and each edge removal corresponds to a path, which takes order E time. So that's the bound. Okay? So that's Edmonds Karp. So you can do better. This is called strongly polynomial, which means it doesn't matter what the numbers are at all. Right? So it's very nice. It's only, and it's sort of like linear algebra too. It didn't. You can solve a linear system in n cubed time, where you didn't care what the size of the numbers were, right? So it has that same property. Okay. So now we have this bipartite graph. We're trying to pair people up. This is dated, but you want to find this largest subset of edges which are 1 to 1, right? So let's try to find one. Okay? Is that subset of edges 1 to 1? No, Ivan is messing around a little bit. So, yeah, okay. So let's make it a little bit cleaner, and there you go. That's fine. So everybody gets matched up here. Does that make sense? So it has to be 1 to 1. This is bad because I took 4 edges. That's what I'm trying to do, get as many of these edges as I can. But I want each person to be matched up to one person. You can think of it as jobs to people. This is sort of what, or whatever, tasks to, people to jobs, say. Okay? Okay? So that's a problem. Okay, so there's a way to do this using a reduction. Okay? What we want to do is we're going to take as an input our matching problem. And what we're going to do is we're going to generate a new graph, which will be the input to a flow problem. Okay? So let's look at this problem. Now I'm going to convert this into a flow problem. Okay, so the way I do that is I just make all the arcs go from left to right. I may direct them from this left set to this right set. I add a source, and I add a sink. Okay? And now, if you look at the solution, this is the solution I had on the last slide. Here are the 4 edges in the middle. Okay? So what I do is I sort of route 1 unit of flow on each one of these edges, and now I could route 1 unit of flow across each one of these edges, and 1 unit of flow across each one of these edges. Okay? So the max flow here in this network, where everybody has capacity 1, is equal to the maximum matching size. Okay? Okay, so now the one problem here is a flow algorithm, if I run a linear program, it may not actually find an integer solution. Okay? It may send half a unit of flow along here and half a unit of flow along here. But the algorithm I showed you before does always produce an integer solution, right? Because you're always only going up to capacities. Okay? So the augmenting path algorithm gives this integer flow. Okay. There's another way to do it. You can actually solve it directly. And what you do here is, what's the maximum matching here? It's kind of easy to see. If I have this graph, what's the maximum matching? Yeah, the edge 8x and the edge by. Okay? So what I'm going to do is do something stupid. I'm going to start with the edge bx. Okay, so now I'm stuck. Right? Like, how do I go from here? I'm just going to say, okay, I'm going to start at B. I'm going to match to somebody. Why not? I can't actually see the whole graph. I can just see my neighbors. I'll match myself to X. Okay? What should I do next? Yes, you should really do something very similar to before. You should be able to undo this thing. So what it corresponds to, I start at A, and I said, I want to match to somebody. So it says, well, the only person I can match to is X. Let me go ahead and try. What happens here? There's a problem. So what should I do with this dotted edge to B? I should unmatch it, right? This is sort of the obvious thing to do. Is like, okay, well, let me try to one of my neighbors. If one of my neighbors is already matched, then maybe I can unmatch that. And maybe from this guy, now I'm like unhappy because this guy says, well, I'm not matched now. Let me try to find a neighbor that was not just unmatched that I can go to. Okay? So you started an unmatched node. What I did is I followed the unmatched edge first, right? And then what I did to come back is I said, well, okay, either that guy's unmatched and I'm super happy I could just match myself, or he's matched. If he's matched, I come back to his partner over here. Yeah. Of the what? Yeah, sort of, yeah. Yeah. I mean, there's a lot. You're saying the set of matchings between the rows and the columns should be on separate things, right? Is it the same? Yes, you're finding a matching on the complete graph between the queens. Yeah, that's right. Yeah, that's fine. Yeah. Okay. So. Yeah. Okay. So. Yeah. He asked if it's a version of the n queens problem. That's a very particular graph. It's a complete graph, and so there's lots of matching, but it's not like a general graph, right? This graph is not the complete graph, for example. Okay. So again, the algorithm looks very much. So you start at an unmatched node, and then you follow unmatched edges in this direction, and then you follow a matched edge in this direction, and backwards, and so on. Okay? Okay. Okay, so here, when do you stop? Like in this case, there's 3 nodes. Is there a matching of size 3? No, right? There's no matching of size 3. Like, how do I know that? Okay? Look, there's a cut. Okay? In this graph, if I start to do a graph search from A to X to B. I can't go from B to anywhere. So, this again I can do with depth first search or breadth first search. I could just search for a path that's alternating. This way it's matched, unmatched. This way it's matched, and then so on. Unmatched, matched, unmatched. And I can just switch which ones are matched and unmatched. Okay? So here there's a cut. Okay? I can't increase the matching size. There's no alternating path from A to V, right? I can go from A to X, X to B, and now I'm stuck. Okay? Okay, but there is some subtlety. What about now? Is there a matching now? Is there a bigger matching now? No, right? Because really what I'm doing is I'm searching in a directed graph where every arc that is unmatched is directed from left to right, and every arc that is matched is directed from right to left. Okay? So now I'm looking at this graph, right? I have to alternate. I have to go matched from left to right and unmatched from right to left. Or I just need to obey these directions, okay, to find an alternating path. Okay? So this one doesn't help me because from A, I can't use this arc backwards, right? And so I can't find another unmatched node. But from C, C is already matched, so it's happy. From Y is unmatched. I can't go backwards. Okay? I can go this way, but I want to follow an unmatched edge. So this is still a cut. Okay? So so this is a matching. This is given a matching. You can direct all the edges from U to V, and you find a path, and then we go back to 61B and do depth first search or breadth first search until everything is matched. Or you output the cut. And this cut is a proof that you can't do better, right? The reason... Okay, so now let me just show you that this is the simplex algorithm in some sense. So you have this thing. You start at a feasible point where n equations are satisfied. For example, x equals 0. And then you view the intersection of n hyperpolyms. And then you drop one equation, and the points on the line satisfy n minus 1 independent equations, and the intersection of... And then you sort of go along this edge of the polytope until you hit a constraint. Okay? Okay, so let me just get past this. I don't need to do this one. Let's do this. So this is the graph, okay? And I'm assigning values to each one of the edges to say if they're 1, they're in the matching. If they're 0, they're not in the matching. Okay? So a solution would be x equals 1, z equals 0, and y equals 1. Okay? Now, these constraints on the right say that z plus y is less than or equal to 1. It says only one of these edges can be matched. Okay, that's what this equation says. This equation says only x, think of them as 1 or 0 variables. So either x plus z has to be less than or equal to 1. Okay, that's the constraint that it's a matching. Okay? And y has to be less than 1. That's a constraint that it's matching to. Now you can do this geometrically. I'm just drawing all of these hyperplanes, and you get some sort of polytope, right? This is the polytope that corresponds to the feasible region for this matching. Okay, so now what do? I start at there's my objective function. I want to increase x plus y plus z. I want to have the maximum size of my matching, so it goes in this direction, as illustrated by the green arrow. And I start at all zeros. Okay? So now what do? Well, I want to increase some variable in the simplex algorithm. So I'm going to increase this one. Why not? Okay, so I'm going to increase it to 0.3, to 0.7, to 1. Okay, so that's like putting in this edge. It's like this is exactly the same thing as this lower vertex choosing one of its neighbors and adding it to the matching. Okay? So now we're here. Now nobody can, now if you look at this graph, nobody can actually choose one of its neighboring edges. Nobody else can because there's going to be some sort of violation. So what's the linear system doing for you? Well, let's think about an augmenting path. So an augmenting path says, well, I'm going to add something to here, and I'm going to subtract something to here, and then I'm going to add something to here. Right? That's what an augmenting path does. So that's what it looks like. It says I'm adding plus 1 to here. So before that was 0. Then I add a little bit of this augmenting path. So I make this one 0.3, and I sort of get down along this edge. I'm moving along this edge. But the direction I'm moving is a direction. This is just a vector in this space. And I'm moving along this direction. And that direction is exactly this edge. So the direction, this augmenting path, is exactly defining this edge in this polytope. Okay? And so you can keep doing it, right? You get all the way to the end, and now you're optimal. Okay? So this augmenting path algorithm is exactly the simplex algorithm in some setting. Okay? Okay, so that's... Oh, yeah. So there's the other thing you can do. You can do everything here, right? Now I can say I have A, B, and C. I can add the constraints to equal the objective function. If I add I can write down the dual variables, and when I add the constraints in this way, I get x plus z plus y. You'll see, right, the left-hand side is I'm adding 1 times that first equation, which is x plus z, 1 times the second equation, which is z plus y. So that's x plus 2z plus y.